Assalamualaikum. Today we group 1 will present about high-speed machining process in CNC machining. Before we get started, let me introduce our group members. Our group has 4 members. First is Izwan Bukhari bin Wahab, Nur Kamalia Hanani binti Bayami, Nurul Aisyah binti Asmi, and myself Muhammad Kaidi Iqbaluddin bin Ishaq. I will start with the introduction. The concept of high-speed machining was first introduced by a German inventor, Dr. Carl Salomon, in the 1920s. It occurred to him that the heat generated at the interface between the cutting tool and the workpiece would peak at a certain critical spindle speed. After that certain point, increasing the spindle speed would reduce the heat in the cut. There are many definitions of high-speed machining, but the commonly used definition is removing the material from the workpiece with high cutting speed or high feed rate or high depth of cut. Compared to conventional machining, high-speed machining operations replace the slow and heavy cuts with fast lighter cut. While the actions appear counterproductive, the change in method actually result in faster production of more accurate part with better surface finish. Then I will have my group member Nurul Aisyah binti Asmi to present the next part.
This is topic review. First of all is application. For the production of rectangular, square, rounded and even 3D projects, CNC machines are also applied in the manufacturing sector. These machines are capable of managing and completing all operations including milling, grinding, turning, boring and reaming. As we can see at the left side, here the product that can be produced by CNC machine. So, the example of application CNC machine results in industry, which is in automotive, aerospace, medical, military, and shipping. Here are some of the automotive components made using CNC machining, which is aluminum wheels, mirrors, wave cover, engine blocks, aftermarket auto part, aluminum brackets, carburetor housing, and air filter adapters. Basically, is the working principle for the CNC machine. A specialist computer is employed in the CNC system to carry out all necessary tasks according to the executive program that is stored in the computer memory. As you can see, this is the diagram that shows how CNC machining workflow. In order to move a tool and a workpiece in a CNC machine, digital instructions known as G code or M code are used in CNC machining. Then the operator set the workpiece in the machine and set the digital instruction on CNC program before beginning the machining process. After that, the system automatically completes the necessary machining operation with help and guidance from the user. Finally is process parameters. The 3 important machining parameters involved in the CNC machine are cutting speed, feed rate and depth of cut, in which this affect the surface roughness of the machine surface. Firstly is cutting speed. The most key cutting characteristic that produce the required cutting motion is cutting speed. Cutting speed refer to rotational speed, whereas cutting velocity refer to tangential velocity. Secondly is feed rate. The feed rate of feed velocity produce the extra cutting motion. The direction of the feed rate is perpendicular to the cutting speed. The main goal of feed rate is to get the cutter closer to the workpiece so that more material can be removed from a larger surface. Thirdly is tip of cut. The tertiary cutting process that creates the required tip within the work material that is meant to be removed by machining. The extra material from the workpiece is removed as a result of the combined action of three cutting parameters is the third perpendicular direction.
Next is application. In this section, we are going to discuss about the effect of parameter involved. As we know, CNC, which stands for Computerized Numerical Control Machining, is a subtractive manufacturing technology that uses program code to control the tool axis movement. All relevant cutting parameters such as cutting tool movement, spindle speeds, fits, and so on are included in the program codes. This characteristic must be considered while developing goods for CNC machining procedures. This factor will ensure the optimization of various sections of the CNC machining process. First is feed rate. Feed rate will determine the machining time and surface roughness of the completed item. As a result, engineers and machinists must understand cutting speed and how it affects CNC machining. The feed rate can be adjusted for the better production rates while losing surface quality. In another scenario, increasing the cutting speed by keeping a feed rate constant, lower feed rate might result in a better surface finish. For the rough cut, a coarse feed rate might be considered. The most important cutting parameter for providing the required cutting motion, it can be applied to the cutting tool or the workpiece by rotating or reciprocating it. In the event of a rotating tool, such as milling, drilling or grinding, or a rotating workpiece such as turning, the cutting speed is determined by the peripheral velocity of the cutter or workpiece. Where neither the workpiece nor the tool spins, the translation velocity of the cutter or the workpiece provides the required cutting speed. The proper cutting speed must be maintained to provide the greatest result from the CNC machining process. Slower cutting rates must be used when machining a tougher material. Titanium, for example, requires a slower cutting speed than steel. Next parameter is depth of cut. A higher depth of cut indicates a higher material removal rate, MRR. As MRR is related to speed, feed, and depth of cut, thus, by using a greater depth of cut, machining productivity may be increased while machining cost can be reduced. Cutting force is proportional to chip load, which is proportional to the depth of cut. As a result, increasing the depth of cut can increase cutting force, which might decrease machining performance and cause a vibration. It also has an impact on chip thickness, chip type, and shear deformation. All of these are indicators of machinability.
Okay, so for performance, high-speed machining process in CNC machining is a process that combines lighter milling passes with a high spindle speed and high feed rates to achieve a very high metal removal rate. So there are three types of performance. So the first one is speed. Speed is a major factor that drives efficiency. High speeds shorten the cycle time of CNC machine activities. One illustration is by moving the spindle home to change tools and then properly placing the cutting tools before cutting it. And the maximum feed and rapid rates can exceed 2,300 inch per minute, which is faster than 3 feet per second. Next performance is precision. Precision machining is frequently the solution when strict tolerance requirement for workpiece must be met. Due to its design and construction, CNC machine can cut with an accuracy of 0.001 inch. And lastly is repeatability. Running from a computer program that controls the machine process with consistency and precision, a CNC machine reliably repeats all steps. As far as day-to-day operation, repeatability issues more often involve the rigidity of the part and work holding or the tooling wear down, not typically the machine's performance. Next is advantage. There are some advantage of high-speed machining process of CNC, which are: first one is a good surface finish. With high-speed machining, cutting temperature are actually reduced. Surface finish is also improved, and the machine spindle and cutter acquire less wear and tear over time. Next is cutting become more consistent. High-speed machining combines the roughing and finishing passes that are normally separate at lower speed. Next is a better productivity. Higher milling speed and feed rate give a higher material removal rate. It can also process hardened part, and its complete surface processing meets the surface quality standard. Next is a smoother and defectless surface. A high-speed milling machine's process use a low mill force, so the workpiece will have a low thermal deformity, and the machining accuracy of high-speed milling is high. Next is a low risk of workpiece distortion. The higher the speed, the lower the cutting force. It also generates less heat that reduces the risk of tool deflection or workpiece distortion. And lastly is efficient. CNC mills feature rotating carousel that can hold up to 30 different tools. These tools are automatically exchanged on the spindle during machining operation, allowing cutting operation to be performed quickly and efficiently. So there are 4 limitations that can be found in high-speed machining process in CNC machining. First one is equipment. High speed require a lot more stopping and starting than low speed. This results in faster wear of your machine's component, such as spindle bearing and ball screw, more maintenance costs, and a larger risk of machine failure. Second is write-off. During this trial and error period, human, hardware, or software error may mean write-off due to the fact that CNC machine cannot be stopped quickly enough to correct the problem. High-speed machining requires specific process knowledge, programming equipment, and interface. Without the right stuff, it can be anything from straightforward. Next is safety. Higher machining speeds and increased wear on part means there is an increased chance of someone being hurt. A regular maintenance check must be carried out, especially things like screw and tools with long overhang. And lastly is expensive insert. Machining at high speed means you will need to invest in the right cutting tools.